So we talked before the break about the fuel model, the live and dead fuels and the different types, but now we're going to talk about how we use satellite information to assess the greenness level of those fuels. So back in, I think, October 1, we actually officially switched to a new satellite for our daily information. Before that, we were using a satellite called Aqua, and the sensor was called MODIS. But now we have switched to the SUMI NPP satellite, and the particular sensor we use to measure greenness is called VIRS, V-I-I-R-S. And that's going to be the sensor of the future because they're sending up additional rockets and satellites in the next couple of years that will also have the sensor on them. So if this particular sensor ever fails in the future, we'll have, I think, up to 3 backups satellites that have the same sensor on them. So we're positioned in OK Fire to go at least through the next 10 years with this particular sensor. So what we use this particular VIRS sensor for is to create daily updates of a particular variable. It actually involves the red wavelength of light and then the near infrared wavelength of light. It's called NDVI, and it's used as a measure of greenness at the surface. And what we get every day is a 7-day, the past 7-day, what they call a composite of that information for each 500-meter pixel in Oklahoma. And what they give us is the highest valid NDVI that occurs during that past 7 days. The reason this is important is because certain days, as you know, there's total cloud cover. So the satellite could not, peer down to the surface. And so the hope is at least one of those 7 days would give clear skies over that particular 500-meter pixel so that we get some valid information. So that's why we use the 7-day composites. And from that information, we calculate something called visual greenness and also something called relative greenness. And they're both 0 to 100% scales. Visual greenness is kind of what your eye would perceive in terms of, 100% would be really, really green. 0% would be, totally no green at all. But what we actually use in the fire model is something called relative greenness, and that's for each 500-meter pixel of land, what is the current NDI value in relation to the max and min that have occurred over a 10 and a half year historical range. And in the research I did this summer, we used the VIRS data from 2012 to 2022. So our max and min values are based on that historical period. So it's kind of a relative index of, is this the greenest it's ever been, or is this the driest it's ever been? And then we have products for both visual greenness and relative greenness. Relative greenness is obviously the most important one that goes into the fire model, but just to compare them side by side, this is for the same date in 2020. At that point, we were using MODIS, but you can see that certain colors change when you go from visual to relative greenness. And this is the information that goes into the fire model. So how do we use the relative greenness in the fire danger model? 2 major ways. We use it to calculate live fuel moisture. Remember, the dead fuel moisture is calculated by the Nelson model, which is solely based on weather and weather conditions. It has nothing to do with the fuel model or anything like that. Live fuel moisture also has nothing to do with the fuel model. It's calculated solely by the satellite NDVI information. And I won't go into any further detail because that would just complicate the process. But another important use of the relative greenness is it calculates the live to dead fuel ratio for herbaceous and deciduous woody fuels, such as occur in hardwood type brush and so forth. So that live to dead fuel ratio is then actually used to determine the actual live and dead fuel loads for those type of fuels. So for example, when these grasses here convert to dead fuels, when that conversion happens and it's dynamic, every week it can change. That's how the satellite information is used to determine the relative proportion of live and dead herbaceous fuels. And the same thing in like the herbacea, in the deciduous woody type fuels. And that's, the hardwood forest can drop their leaves and turn brown and so forth in the wintertime. And so that's also how relative greenness is used as well. So two major uses for relative greenness. And again, just to show the importance of live fuels, fires tend not to go where there's a lot of green live fuel present. Here's a typical over the course of a year scenario of how relative greenness responds. This was taken from Osage County, our 4-acre site in 2009. But you can see during the winter time, the live to dead fuel load is pretty low. It's on the order of 20% or so. And then you get the green up in the springtime with minor variations, and then you get senescence in the fall, and then drops off to lower levels. So this time of year, we have more live fuel than dead fuel. This time of year, we have more dead fuel than live fuel. To show the importance of relative greenness with the same fuel model and the same weather, these were examples of a forecast for Lahoma and Blackwell. They're mesonet sites that are fairly close to each other. So basically, we're experiencing the same weather, and they have the same fuel model. Notice, though, Lahoma had a fairly low relative greenness with respect to Blackwell, which was at 59%. And notice how the fire danger for that same forecast period is greater for Lahoma than it was for Blackwell. And that's because, based on the greenness level, there was more dead fuel at Lahoma available with Model T than there was with Blackwell with the same Model T, because there's more live fuels when the relative greenness is higher. So that's what the satellite is used for. It's used to adjust the relative proportions of the live and dead fuels for both herbaceous fuels and the woody deciduous type fuels. So basically, the satellite is looking at the composite vegetation in each 500-meter piece of land. And if you happen to be in an agricultural or urban area, the nearest mesonet site, the RG value for that site may not properly represent the greenness of the wildland fuels in your area. And I can show you that when we do the demo of the current relative greenness map. But here's some examples from the past. This was in March of 2012. You can see the winter wheat belts here in the dark greens in this area, part of the state. So if you were a fire department, say in Hobart, the pixel that the mesonet tower was in was measuring 85% relative greenness. So would you want to use that with the fire model charts and tables to predict fire danger for the wildland fuels in your area? Probably not, because that's basically saying you basically have pretty much all live fuels in your area and no dead fuels. But if you look at some of the surrounding areas for which you may have responsibility for wildfire suppression, such as the Wichita Mountains here and some of the areas out to the west, that would not be representative of those fuels at all. So you want to choose a nearby station that's basically would have similar weather, but would have a relative greenness more representative of what you're seeing with your wildland fuels. So you might want to choose Medicine Park to use with your charts and tables for the fire danger model, or you might want to go to Mangum at 46%, but to be, even more conservative, you'd probably want to go where the lowest relative greenness value is. And the same thing for Kingfisher. If you were a fire department in the Kingfisher area, you'd probably want to go to one of these Oklahoma County stations or some that have, much lower relative greenness values. The reverse type of thing happens in the fall. This was October when the winter wheat and other agricultural crops have been harvested. So these red areas are basically either bare soil or stubble. And so they certainly don't represent the greenness levels of your wildland fuels. So in this case, if you were a fire department in Marshall, you'd probably want to use one of these nearby Payne County stations, which have, greenness levels of around 40% to be more representative of the wildland fuels, because with such low relative greenness, you'd be getting high fire danger pretty much every day there, which would be totally unrealistic as compared to what what the wildland fields were really doing at that point. So I hope you understand the point I'm trying to make. So it's important to know the current greenness conditions of your wildland fields and to choose a nearby mesonet station to use with the fire danger model, and in particular, the charts and tables, whose relative greenness best reflects what you're currently seeing on the ground. And when we do our group exercise in the next segment, we'll make this very practical on how to go about doing that. So let me now go to the website to show you where you can get our relative greenness products. Let's go back to the home page. So if you scroll down, at least for the two stations that you have on the home page, if you go to the very last variable in the fire danger table, you'll see relative greenness. For Stillwater, it's at 17%. For Marina, it's at 10%. If you wanted to see the statewide map, you could click on that link and it'll show you most of the state is super brown at this point. There are exceptions, but by and large, this is a very dry time of year. And so, you know, given appropriate fire weather conditions, fires can break out really at any time. I want to next show you this other zoom map, which is a corresponding map to the default fuel model zoom map. But again, you can zoom into your area and then see individual 500 meter pixels what the relative greenness is doing in your county or area like that. Now, I mentioned there's probably places that you wouldn't want to use the mesonet site for your fire danger calculations. And one of the examples down here in southwest Oklahoma, for example, would be Hollis. You can see most of the wildland fuels around Hollis are in the reds and oranges, but for some reason, Hollis is reading 67% relative greenness, and that's probably because the 500 meter pixel that the Hollis mesonet tower is in is next to a winter wheat field that's very green at this point in time. You can see there's these various areas that are pretty green, so that's probably what is influencing the Hollis mesonet site. So if you were a fire department in this county here, you would not want to use Hollis for your table and chart products. You'd probably want to go to Mangum, which is at 3%, or even Altus at 37%, or Eric, but that's not good either. That's probably being influenced by a winter wheat field as well. You can see Elk City is down to 14. So that's a good example of a place you wouldn't want to use that site for the fire danger products. Another example would be El Reno. That's at 62%, probably because it's really close to a winter wheat field, and that's reflecting the greenness there. So you'd probably, if you were a fire department in El Reno, you'd probably want to use the Yukon station to represent your fire danger chart and table products. If you're in Payne County, another example would be you wouldn't want to use Lake Carl Blackwell, but you could probably use any of these other three stations to be representative. Another one that I noticed last night is down here in southeast Oklahoma. Valiant is at 70%, whereas everything around it is like super dry, like cloudy, 15%, Idabel 9, 21%. So if you were in a fire department at Valiant, you wouldn't want to use that station either for your fire danger chart and table products. So I think you can see the point I was trying to make. You need to choose a mesonet site that has a greenness level appropriate to the greenness of your wildland fuels that you're observing. So let's now go just to show you that.
Katie, we have a question. I think it's related to relative greenness. So this comes from Lance, and he's asking, is the difference between Lahoma and Blackwell due to crops or maybe more recent burns, thus more green and less dead remaining?
Well, that example I showed you was from probably a decade ago, so I have no idea, you know, as far as recent burns or anything like that. But it basically, that the differences there were basically due to the fact that, you know, the relative greenness was different at the two stations. And I know the Blackwell station, I forgot what time of year it was, but the Blackwell station is close to some winter wheat fields and, you know, crop areas. So that could have been influencing why they had a lot higher relative greenness as compared to Lahoma. Okay, so where was I? Okay, I wanted to go
You
to
were
the,
headed back to your PowerPoint, I think.
no, I wasn't. I was still in the demo here.
Okay.
I want to show you in the animated map section that you can also animate a relative greenness in this pull down menu. You'd have to go to the past time mode, of course, because we don't predict what the satellite's going to see in the future. But you can choose relative greenness. And then like if you wanted to animate the past, 8 weeks, for example, to see how the dry down has been proceeding over time, you can see that the map slowly gets redder and redder over time. Here's the each day as it goes through the animation. You can see the southeast was pretty green, but now in the last frames of this movie, it really starts to drop in greenness level. You can see there. But Valiant goes way up from what it was before. So I think it must be being influenced by either fescue that's getting really green, or there's some winter wheat fields in that area. So that's where you can go for that. And then also in the chart section, you can also plot relative greenness in past mode. And you can select relative greenness. And let's look at, say, the past 16 week, or let's go past 8 weeks at Stillwater, how the greenness level has changed. Well, that's not too dramatic. Maybe we need to go back a little further. Let's go past 16 weeks. Yeah, there you can see the steady drop in greenness at the Stillwater site. So you can do those type of things in the charts in the past mode for relative greenness. So now let me go back to my presentation. So now, as far as weather, we talked about that in part 1, but basically we get the past and current weather conditions from the Oklahoma Mesonet. And then we use the 84-hour North American mesoscale model to go 84 hours into the future. So as I said at the beginning in the first talk, basically what we mean by fire danger, it's the ability or potential of a wildland fire to start, spread, resist control, and do damage. When we talk about fire danger rating systems, there are some assumptions and limitations that you need to know about, especially if you're the technical types that I know some of you are. It's not meant to be used for fire behavior on a specific landscape. In other words, taking into account topography or, a very small area. Remember that what we're doing in our fire model is using 500-meter square pieces of land for our calculations. So within each fire danger rating area, in other words, our 500-meter pixel of land, we assume the fuels and the distribution of fuels are homogeneous. The weather over that 500-meter pixel is homogeneous, which of course is a more likely assumption than it would be for fuels. And also the topography is assumed homogeneous. So basically what the fire model is calculating is, given the homogeneity of the fuels, weather, and topography across their area, this is what you would expect on the average for fire behavior in that area. It's not meant to be used on a field by field basis. There's other programs that some of you know about, like Behave and so forth, that would do calculations on a field specific level. So you're getting basically the average fire danger over the rating area. But it has a great, number of useful purposes, fire danger rating. It can help you provide public warnings. It can set your preparedness levels if you're in a fire department or state federal agency. It can provide a good indication of the difficulty of fire suppression over a wide range of conditions. And it helps you make wise management decisions in both real time and the future. What is a rating system then? It's a fire management system that integrates selected fire danger factors into one or more qualitative. An example of that would be high fire danger, medium fire danger, low fire danger, or numerical indices that are actually calculated based on, a physical model of fire danger. And that's what we use in OK Fire. There's 4 numerical indices that we'll talk about that the fire model produces. And it's based on the 1988 version of the National Fire Danger Rating System. So now let's talk about the outputs of the fire danger model. First one to talk about is called the spread component. That relates to the forward speed of the head fire in feet per minute. And again, that's just for the average over that 500 meter pixel of land. There could be, based on the fuel distribution, areas where the spread component is faster. There could be areas where it's slower, but the average spread over that 500 meter pixel of land would be this particular number. Then there is something called the energy release component, which relates to the heat release in the flaming zone of the head fire. And we don't use that much in OK Fire like they do in the Western US, but it is used as a input to what's called the burning index. And that's the variable that we stress the most in OK Fire, because it's calculated using inputs of the spread component and the energy release component. And it relates directly to fire line intensity, how difficult it is to control the fire. And it's scaled such that if you divide the burning index by 10, you get the flame length in feet of the head fire. So a burning index of 40 would mean a flame length of 4 feet. A burning index of 100 would be a 10-foot flame length, and that would be at the head fire. And again, that's just the average for that 500 meter pixel of land. So let's go back to the second week of the Ray fire in April 2018. Here was where the fire was located. Here you can see spread components in feet per minute. So some of these are approaching 300, which if you think of a football field, that would mean the fire is moving the length of a football field in 1 minute. So that's pretty fast spread behavior there. Energy release, again, is not anything dramatic, because in this part of the state, a lot of the fuels are herbaceous and they don't put out as much heat per unit area as some of the heavier fuels would in eastern Oklahoma. But so that's why we really don't talk about that particular variable in OK Fire. But the burning index, which is based on both of them, is the most important. And here you could see we had burning indices of approximately 150, which would be a 15-foot flame length on the average at the head fire. So that's what that showed for that Ray fire. The typical Forest Service interpretation of burning index is shown on this table for different ranges of burning indices. Here's less than 40, 40 to 80, 80 to 110, over 110. It shows the difficulty of controlling the fire. And this information is in some of the documents that's on the website that I showed you where to go in part 1 yesterday. But under 40, generally you can attack the fire on the head or the flanks using hand tools. Once you get above 40, it's too intense a fire to use hand tools, but you can use equipment, heavier equipment can be effective. Once you get above 80, serious control problems, control efforts at the firehead will probably be ineffective. And once you get over 110, control efforts at the head of the fire are ineffective, and you can get major crowning and spotting and major fire runs. And in OK Fire, we break these 4 categories into 5 categories. We break this first category into a low category, which is burning index 0 to 20, and moderate, which is 20 to 40. And then we call this high, severe, and extreme. And on the home page, in the fire danger boxes here for whatever sites you've chosen, we color code the current fire danger according to, this classification. So in this case, the burning index was well below 20, so that's why it's showing low fire danger, and it is colored green at that point. So what do you typically look for when you're looking at burning index? Well, this, as we showed yesterday with the 3, temperature, wind speed, and relative humidity, the typical behavior in kind of a stable weather regime is that you get the highest fire danger in the mid-afternoons, and then it lessens over in the overnight hours to kind of a minimum around sunrise. But there are exceptions, fronts moving through, or stronger winds, or other things going on. So if this were a forecast chart and you were at Burbank, you would see clearly that of the next 3 days, that tomorrow, which in this case was Friday, would be the day to be on the lookout for, because this has a lot higher fire danger than do these 2 days. Another thing you can look for is continual periods where the burning index is above 40. So here was a multi-day period when the burning index was above 40, and that means you're going to have trouble even at nighttime with fires. And then it really peaked on this particular day. For those of you who were in Oklahoma, this was actually Good Friday in 2009, and there were multiple big fires in Payne County, and Highway 51 was shut down west of where I live in Nottingham. And so a lot of activity going on that Good Friday, and Rob probably remembers that as well. So those are 3 indices. The 4th indice is called ignition component, and that relates to if a firebrand gets tossed out from the main fire, what's the probability of another reportable fire resulting from that firebrand. It's a scale, again, from 0 to 100%. It says nothing of the intensity of the fire, which is what the burning index covers, but it says a probability. So let's look again at the Ray fire, and here you have 92% probability that a firebrand wafted downhill could start a new reportable fire. And here's 100% probability. And I think this is really the first time I've ever seen the ignition component actually be 100%. I'm sure there's times I've missed, but that definitely shows you how bad a day that was, April 17. The 1988 system added what's called the Keach-Byram Drought Index to the fire danger rating system. It's an index that ranges from 0 to 800. It's a very simple model that's only based on the daily rainfall and the temperature at, I think it's like 4 p.m. Standard time. So it's very simple. And a value of 0 means that the soil profile is holding 8 inches of water. A value of 800 means there's no water in the soil profile. Yeah, and this is, quite unrealistic for a lot of Oklahoma soils, because some of our Oklahoma soils, there's no way they can hold 8 inches of water. This was developed, mainly for the southeastern United States at the time, but we still use it in Oklahoma, based on that 1988 system. So here's typical what a KBDI map looks like. This was during the Ray fire as well, not particularly high in the fire area. And generally, we think anything over 600 is a kind of a cause for concern as far as KBDI. So this was only moderate levels of KBDI. But we talked yesterday about this new variable that we put in Mesonet about three years ago or so, the 16-inch plant available soil moisture, which is also an indication. And it's actually a measurement from our Mesonet soil moisture sensors of what's in that soil. So this is bound to be more accurate than a simplistic model based on, temperature at 4 p.m. and 24-hour rainfall. And you can see for the same day, this was July 11, 2019, how they can differ at times. If you were just looking at the KBDI map, you'd say, hey, there's no cause for concern of any wildfires because the values are nowhere approaching 600. But if you look at the same 16-inch plant available soil moisture map, you see there's still areas in the oranges and reds that indicated areas where, big growing season fires could break out given there was an ignition source and appropriate fire weather conditions. So definitely during the growing season, we recommend you look at this particular map. Even though it's not used directly into the fire danger model, it's still a good standalone tool to look at as far as the probability of having a large growing season wildfire. So let's look at the fire danger model itself. It's run every 15 minutes with the Mesonet data. It produces colored maps to that 500-meter resolution of the 4 indices produced by the fire model. That's burning index, spread component, energy release, and ignition component. It produces colored maps of the 4 categories of dead fuel moisture every 15 minutes. Live fuel moisture, because it's based on the daily satellite information, is updated only daily. And KBDI, since it's based on daily weather information, that's also only updated daily. And then, of course, we have charts and tables as well for the mesonet sites. So let's answer some of these questions that we posed at the beginning. What are the three major physical determinants of fire danger? Well, the first one was the fuel loading, the types of fuels we have. Are they herbaceous? Are they woody? Is it brushy or mainly grasses? And then how much live fuel is there versus how much dead fuel is there? The second one was fuel moisture. What are the fuel moistures for the live fuels, the different live fuels, and also the different, and then the dead fuels that are out there, which would again be the average for that 500-meter pixel, and at least for the live fuels, because that's based on satellite. Actually, the dead fuel moisture is calculated at each mesonet site and then interpolated to each 500-meter pixel. So that's a little more site specific than the live fuel moisture would be. And then, of course, the third physical determinant would be the weather conditions. What are the differences between dead and live fuels? Dead, as shown in this diagram here, would be anything that lacks any degree of greenness. So these would be dead fuels. This little greenery here would be an example of a live fuel, as with this over here. How do 1 and 10-hour dead fuels respond differently to weather conditions than 100 and 1,000-hour fuels? These smaller size diameter fuels, like grasses and small pieces of low diameter wood, can respond very quickly to changing weather conditions, whereas these thicker fuels, 100-hour and 1,000-hour, they respond much more slowly, and they're mainly useful as indicators of extended wet periods or extended dry periods. What is the fuel model? It's basically a mathematical representation of representing a landscape of interest to you. How can I change it on OK Fire? We already showed you how to do that. Go to the station fuel model options link. Why is relative greenness important? It's important in OK Fire for two reasons. It calculates the daily live fuel moisture, and it also calculates the distribution of live and dead fuels as far as the herbaceous fuels as well as the deciduous woody fuels. And then finally, this is very important. What fire danger variables do fuel model and relative greenness influence in OK Fire? There's only 4 variables that they influence, and that's the 4 indices that the fire model puts out, and that's burning index, spread component, energy release, and ignition component. If all you're interested in is like dead fuel moisture or live fuel moisture, that's based, solely on weather conditions as far as dead fuel. Live fuel is based on satellite. But if you're interested in actual fire behavior, numerical indices like burning index, then fuel model is very important, as is relative greenness. And we'll show that practically speaking in the next section after our break. So let me now go back to the website and just show you a few things of the fire model output. Let's go back to the home page again. So going back to these tables for Stillwater and Marina, you can see right now with Model T, the burning index is 49. So that's considered high, and that's why it's colored orange. The Marina is at 50. So a fire could break out, and it would have, high fire danger at this point in time if there were an ignition source. That's what that's saying. Ignition component, pretty low at this point, only 17%, 16%. And then, of course, you can look at the current map of burning index by clicking on the link, and you can see certain parts of the state have higher than others, particularly up here in northwest Oklahoma, Woodward, and some of these dark red areas. Not only because of the fuel types, but also because of the stronger winds up there today, and probably lower 1-hour dead fuel moisture as well. And then you can look at a spread component map, for example, and see where the high areas of spread are expected. The highest one here is about 123 feet per minute. The ones in Payne County are around 60 to 80 feet per minute if a fire were to break out. And that's why maps are kind of good to look at, and not just necessarily sticking to a table or a chart, because especially if you have responsibility for a wider area than just your city, or, you know, if it's like a county or a regional area, you can look at some of these maps and see, in my area of influence, there's quite a bit of orange areas here and so forth. Whereas if you were just looking at the Hollis Mesonet site, you would say, yeah, there's no fire danger there and no spread component. It's only 4, no big deal. But, you know, looking at maps can allow you to assess, you know, your whole county and regionally what's going on. Now, let's see, where else did I want to go? Let's go to the animated map section just to show you, you can animate the fire danger model output. So let's go down here, choose burning index, and then animate the map. So going through the forecast period, so you can see it lessens fire danger overnight tonight. Now we're going into Friday. Again, pretty bad in the northwest Oklahoma in spots. Now we're going into Saturday afternoon. So it's kind of this up and down pattern. So the good thing is if you were fighting a fire one of these afternoons, the intensity would go down as you approach sunset and overnight, which would give you an opportunity to control the fire. So it's not like you have an extended day and night high fire danger period. So, and then you can do the same thing for example, if you wanted to animate spread component. You can do that through the period. There's some in the hundreds up here. So again, what I like about the fire model output is it's a great integrator of everything. It integrates the dead fuel moisture, it integrates the live fuel moisture, it integrates the fuel types and their greenness levels. And so if you had to just look at one variable, assuming you're using the right fuel model and relative greenness in terms of the chart or table products, that's really the one best variable to look at. If you're looking at just map products, then, you know, you can just look at these maps and see your county or whatever, you know, what the conditions are just by the colors. So that'll help you for that.
We have a quick question regarding ignition component. Alex wants to know if that's based off of shaded or exposed surface fuels.
Well, that's not my area of expertise. It's just whatever the equations were for the National Fire Danger Rating System that we acquired, but I would assume would be for an unshaded area. That would be my assumption. I want to show you, you can also do burning index chart. So this is Model T for Stillwater. Let's see what that looks like. So again, that day-night behavior, there's hours during each afternoon that are above 40. Today and Sunday look like, you know, of the next 3 days, looks like, you know, Saturday is going to give us a little respite, but that's what that looks like. You can also plot side by side. For example, if you wanted to plot spread component and burning index together, you can do that. See that they kind of go side by side, but the blue is the spread component. So the max we're getting according to the fire model would be about 60 feet per minute on tomorrow afternoon. So there's really a lot of good stuff in OK Fire. I mean, it's amazing the stuff that we have in here. And so it's a really great tool to use. What else was I going to talk? I think that's all. Let's just, for the fun of it, go to Woodward, because they seem to be having the higher fire danger today. And let's see what that forecast would be for Model T. Yeah, quite a bit higher fire danger, up to 90 tomorrow, and then dropping off a little on Saturday and going up a tad on Sunday. But so these are places that you can get the fire danger output on the OK Fire website.